Hello everyone, it's me Nugroho. I want to present my homework 2, number 2 about PID control. To talk about PID control, we need to look back at a feedback controller. A feedback controller is a control system that continuously compares the desired output or set point with the actual output measured by a sensor and adjusts the system to match the desired output. The sensor is can be any sensor. It can be an analog sensor or any digital sensor. The feedback loop is used to monitor and adjust the system inputs, helping maintain a stable output even when the condition change or any disturbance occur. This is the some mind map from Armstrong K, scientists and an introduction for scientists and engineers about feedback system. A simple feedback system can be divided or classified into three. The first of all is on-off control, and then proportional control, and then PID control. And then for the on-off control, we can divide it into three subcategories, which is the simplest one is the on-off control, and then on-off plus dead zone, and then hysteresis. This is for the on-off control. And we right now we can compare open and closed loop system. This is from a controller to process. Commanded variable, any commanded variable can be inputted, can be as input for a controller, and then after the control, the actuating signal can control the actuator, and then we can make it to the process, and then the control variable can be measured. And for example, an example for open loop, we can use a dishwasher. So when there is a dirty plates, and then we can put it on the dishwasher, and we can set the timers. This is the timers, the commanded variable like this, and it can be also as a controller. And after the timer is on, and then the controller, the electricity is on, the the actuating signal from the timer and the electricity, we can command water jets to pour some water to wash the dirty plates, and then uh, the dishes can it should be clean, but whether it is clean or not, we don't know. It just based on the timer, so that's what it's called as a open loop control. Sometimes open loop control is defined as typically reserved for a simple processes that have well-defined input to output behavior. So this is based on the well-defined input to output behavior. Not all the case can be inputted to disposer. Not all the plates and dirty bottles, dirty glass, put it on the dishwasher and we get the same output. Not like that. That's the open loop system. And for the closed loop system, we the difference of open loop and closed loop mainly in this feedback. For arbitrary process, though, an open loop control system is typically not sufficient. This is because there are disturbances that affect our system that are random by nature and beyond our control. There is some disturbance if we get an open loop control and then we get a disturbance. We need some feedback to be collected, and then we can sum it with the commanded variable, and then we get an error terms like that. So the difference of open loop and closed loop control is based on the feedback line in this, like in this diagram. And what is disturbances? Disturbances like, for example, for the pole. If I want to put a ball inside a bowl like that, I don't need, if the ball is not inverted, then I don't need any control system to measure the to be placed, the ball to be placed in the ball position is in the middle of the ball, because gravity will keep the ball inside and in the center of the ball. But when I inverted the ball, and I want to put the ball in the middle of it, the ball will fall down, and we cannot set the ball at the center of the ball. So we need a feedback control system to keep the ball on the ball. So set the set point is the desirable position, and then we can use the control algorithm to control the fan dynamics, and then the fan dynamics can uh, move the ball if there is some movement from the ball to right side, left side, front side, or back side. So the ball can be placed or can be moved to the desired position. And after the fan dynamics push the ball, we have the actual ball position. And then we can feedback it to the control algorithm with any radar sensor or ball position estimator. This is just a figure to explain about feedback control system. And based on the Okatas in 2010, Okata states that most industrial controllers may be classified according to their control action as there is 6 classification based on Okata: 2 position or on-off controllers, and then proportional controllers, intercurrent controllers, and PI controllers, PD controllers, and PID controllers. This is one example of on-off controller, as I mentioned before. This is the on-off controller. A is block diagram for on-off controller, and with B, this one, it has a differential gap. And this is the timing diagram of the differential gap like this. Okay, this is the on-off controller, and for the PID controller, the reason why on-off control often give rise to oscillation is that the system overreacts since a small change in the error makes the actuated variable change over the full range. This effect is avoided in proportional control, where the characteristic of the control is proportional to the control error for small error. A PID controller is very useful and is capable of solving a wide range of control problems. More than 95% of all industrial control problems are solved by PID control. And this is the table that uh, about when to use the PID control or PI or PD or PID. In this table, I'm not mentioned about PD controller. And P is usually for a slow response and system tolerant to offset. When the system is tolerant to offset, we can only use the P controller. And I and D is not usually used alone. So we have to combine it with P controller. Sometimes it's PI or PT controller, and the best one is PIG. P estimates present, and then I estimates back, and then D estimates about forward. So this is present, this is P, and the past is I, and the future is D. And this is the block diagram. So the set point is it's almost the same with the problem in the inverted pole problems. And this is the block diagram for this is the set point or desired pole position in the previous diagram inverted pole. And we have a summation block with, and then the set point like in this, after computing from the feedback, we can have an error value or it. And this is the PID controller. P term for proportional, the proportional term equals Kp times E of t. The Kp is the proportional gain, and for the integral term, Ki integral from Ki times integral from 0 to t times E of t with respect to t. And then for the derivative term, uh, Kd for the derivative term, the Kd times the derivative of E of t with respect to t, which is Kd is the derivative gain. And after we sum all of the controller, all of the term, we can get the control signal, and we call it process, and the output of the process is the yt, and then from the process like this, we move it again to the sum with the set point. This is we uh, minus. And this is the PID controller. UT is the control output, the signal to the system actuator, for example. And ETS is the error at time t, E of t, which is the difference between the set point and the process variable. E of t equals set point minus process variable. This is the PID step response. We have the settling max, settling mean, rise time, peak time, settling time, and peak. We can get this response, the information from the step response, from the MATLAB directly. So the settling, what is settling time? Settling time is defined as the time taken from the transient response to reach and remain within a certain percentage of the steady state or final value. The rise time is the time it takes for the response of the system to go from 10% to 90% of its final value or steady state value. This is the rise time. The rise time from this to this. And that's the peak time. Peak time is defined as the maximum, as the time the system takes to reach maximum overshoot. This is also the step response. And there is also terminology about dam, which is over dam, under dam, or critically dam. Dam is mentioned because the damping ratio or zeta, or this is zeta, small Greek letters, C small Greek letters. We can get under dam response like this one when the zeta is less than 1. We can get the overdam response like this one if the zeta over 1, and we can get the best of it, which is critically damped, we in the zeta of 1. And then according to the PID closed loop response, we can by the gain from the proportional, integral, and derivative. This is the constant. Proportional gain, integral gain, differential gain. We can classify and we can tuning the um, tuning the KP, KI, KD based on this table. When uh, we want to decrease the overshoot, so we need to increase the KT like this. If we want to decrease the rise time, and then we need to adjust the KP, KI to be lower than the first time value. Like this. This is the closed loop response based on the PID. Okay, sorry for that. So this is the examples of PID on linear plans. PID on linear plans. I want to give an example about mass spring damper system or MSD. Usually it's illustrated as this one. There are mass. This is mass, and then this is spring, and then this is the damper P, and we have force in this, and the displacement of X. In mass spring damper system, we have three elements, which is mass. The equation for mass is force applied F equals to mass times acceleration, which is same also as mass times displacement double dot, or m times x double dot. And for the spring, we have force equal to k times x, with k where k is spring constant and x is a displacement. And for the damper, we have this equation: F equals P times V, or equals to P times X dot. MSD system consists of one damper, one spring, one mass, and one actuator. The free body diagram of this, after summing all the force and applying Newton's second law, we get this one. F minus B times X dot minus K times X equals M X double dot. This is the free body diagram. So the force like on that direction is an F in that direction minus this and this minus this equals to the displacement of the mass. So from the previous equation, we move the F. It will be equal. This is the F equals to M times X double dot plus B X dot plus Kx. By applying Laplace transform from this equation, we get ms square x plus bsx and plus kx. So if we put x together, we get this equation. And from this equation, we can get the transfer function of this uh, open loop system, open loop transfer function of the system. So g of s equals x over f equals 1 over ms squared plus bs plus k. This is the same. So this is where f is force. This is the input, and then output is x for the displacement. One thing to be considered is that this is the frictionless system. This is the ideal condition that won't happen in the real condition. So applying PID to MSD system, we will get this transient response, and this one is the steady state. Uh, okay, I will show the MATLAB experiment. This is the experiment I use in the MATLAB. We have we define the M mass as 3.6 and K 1.8 and B 0.5. This is the numerator and this is the denum, and G is the transfer function of num and denum, and then we have the step G to figure out in the figure to, and then I will show the fourth trial. This is the first one with the Kp of 1, Ki 0, Kg 0, the gain of the K proportional integral and derivative. And for the second try, Kp will be set at 10, Ki 0, D 5, and so on. And then we have the feedback like this one. Okay, I will run the first trial. This is the first trial. So this is the output after feedback, and this is the first one. And if I comment this out, comment and uncomment this one, and I run, this is what happened. This is uh, the second trial. the okay, this is the second trial, and this is the third trial. I will run, and the blue one is the response of the third trial based on this setting. And the last one, this one is our last output. So we can use the peak response. This is the peak response, peak amplitude. This is from the 1, 2, 3, 4. This is the overshoot. This is the overshoot, and then we can show the rise time also. Rise time. This is so crowded like that one. And then for sorry, for the settling time. This is the settling time. Settling time faster but not good. This is the fourth one. It's quite good. Okay, to summarize the trial, this is the rise time, transient, settling time mean, settling time max, overshoot, and peak time. We can get this based on this code step info. Okay, and this is the reference that I use for this presentation. The first one is feedback system from Enstrom and Okata, Modern Control Engineering, and Brian Douglas, Fundamental Control Theory online. We can get the free ebook for the three first chapter of that Brian Douglas wrote. And this is the best, yeah, one of the best web that I read. And CTMS, this is my main reference also. And for the MATLAB, I use this reference. Okay, thank you so much for your attention, for your kind attention, and see you in the next video. Thank you.